Oh, good catch. Here we are. Woo. There's some empty seats out there, so for those of you watching at home, we just talked about several questions that will be on the exam. Never stops being funny to me anyway. So I told you how imine formation and imine hydrolysis are exactly the same, only backwards. That the mechanisms, the arrows are going to be different, but the intermediates will all be the same. Recall that for imine formation, the amine attacks the carbonyl carbon at the same time as the pi bond is breaking, at the same time as lone pairs on the oxygen are attacking the proton from your acid catalyst, at the same time as you're breaking the bond between proton and conjugate base. That gets us to this positively charged intermediate. The positively charged nitrogen is called an ammonium ion. The conjugate base of our acid deprotonates the ammonium ion to get us to the neutral carbonylamine, whereupon the acid protonates the oxygen, what used to be the carbonyl oxygen, to convert it into this oxonium ion. So maybe some of these words would be useful if I wrote them down. Ammonium and oxonium. And then the highlighted group in orange is a good leaving group. The nitrogen, neutral nitrogen, acts as a kicker-offer to get to this iminium ion, which is deprotonated by the conjugate base of our acid, thereby generating the imine product. I is for imine. Somebody pointed out in office hours today there actually is a textbook, or not a textbook, a board book for babies called Organic Chemistry for Babies. I can't endorse it, I haven't read it yet, but what we saw was kind of interesting. Carbon is a very special atom. So that's imine formation. Now notice that imine hydrolysis proceeds in exactly the same way with exactly the same intermediates. You start with the imine, you protonate on the nitrogen using the acid catalyst to generate this iminium ion. That iminium ion is reactive enough for water to attack to form this oxonium ion, which is an example of a tetrahedral intermediate. We then use the acid, conjugate base of our acid to, sorry, the sound's picking up every motion I make. Sorry about that random thumping. I guess you'll just have to live with it. The conjugate base of the acid removes a proton from the oxonium ion to generate the neutral carbonylamine. Then the neutral nitrogen attacks the proton to generate the ammonium ion again. And then the neutral oxygen is a good enough kicker-offer to kick off the ammonium group as a leaving group, and that gets you to your starting material, your aldehyde, and your imine. Okay? That's imine formation and imine hydrolysis. The reaction's totally reversible. What drives it forward is going to be, among other things, whether or not you're synthetically removing water. And if you remove that, you can push it forward. If you do the reaction in an excess of water, that will tend to hydrolyze the imine. Okay? Now, we don't want to spend too much time on enamines because they're basically the same as imines. The difference, though, comes to the iminium ion. It comes in the step with the iminium ion. So let's just take enamine formation, recall, will happen with aldehydes or ketones, but your amine ends up being a secondary amine. And you'll see why this is different as we draw the mechanism. So I think it would be a good exercise for you. Every time I do this, students hate it, but I'm going to do it anyway. It would be a good exercise for you to use what we've drawn above to get all the way to the iminium ion. I'm not going to repeat that because it's above, and all you have to do is just repeat it only The nitrogen's got 2 R groups on it. So get all the way to the iminium ion. And notice that what we did above, at the step that we had the iminium ion, the conjugate base of our acid could remove a proton from the iminium ion. There's no NH bond to remove. So when you use a secondary amine, you can't get to the imine product because there's no NH bond to remove. What happens next requires us to have actually drawn what that R group is. So let's just for fun suppose that the R group is CH3. So I'll redraw this molecule with the CH3 on there. There's no NH bond to remove in the iminium ion, but there are some CH bonds here on the methyl group. Notice that this methyl group is alpha to the iminium carbon. I'm still going to call it the carbonyl carbon because that's where it came from. And we will see, for reasons that we'll talk about a lot more in an upcoming chapter, that protons that are alpha to carbonyls are more acidic than you would expect for your normal everyday CH bond. And in this case, the reason for that is that if I remove the proton, and it doesn't need to be a very strong base that removes that alpha, what I'm going to call an alpha proton, if I remove that alpha proton, pay attention to the conjugate base. Or rather, pay attention to what's left behind when that alpha proton is removed. So I'll draw the product of that alpha proton removal here. There would still be 2 protons there, and the alpha carbon is negatively charged. What do you notice about that negative charge? 351 word that begins with R. Resonance. R is for resonance. I wonder if that's in the book for babies. You can move this lone pair to be a pi bond between alpha and the carbonyl carbon. If you stop there, you'd have too many bonds to carbon, so you have to break the carbon-nitrogen pi bond, move it out to a lone pair on the nitrogen. And these two are resonance structures of each other. The major contributor is probably the neutral one. Both of these are valid resonance structures for the enamine product. So the difference between making an enamine versus an imine is that with the enamine, there's no NH bond to remove, so instead you remove the alpha proton to get to the neutral enamine product. Okay? Enamine hydrolysis is going to be exactly this, but backwards. So for example, if you started with an enamine, I would actually draw this resonance structure, and then I would show this lone pair electrons attacking the proton on the acid catalyst that's regenerated in the final step. And that will get you to the iminium ion, and then you can go backwards from there. Your text doesn't say a lot about enamines. You might expect them to be somewhat nucleophilic on the alpha carbon because of this resonance structure, and they are. And in fact, a few years ago, the Nobel Prize in Chemistry was awarded for reactions involving enamines as nucleophiles. So it's a pretty big deal, though it's beyond the scope of an introductory OChem class. Questions about enamines or any of these mechanisms? Will they be on the test? Yep. All right, so a couple more things about imines. They're really, really important in biology. As I said last time, the Maillard reaction that results in that delicious golden brown appearance of our baked goods involves, as a first step, imine formation. There's other things that happen. Some of the symptoms associated with diabetes are as a result of something that's called glycation. Ever heard of glycation? Folks that have diabetes sometimes monitor something called HbA1c. Anybody know what that is? That's a measurement of how much of your hemoglobin has been glycated. So I want to show you what that means, because if you don't monitor your own HbA1c, you as a physician sometime in your future may be monitoring somebody else's. And it would kill me if you didn't remember that at some point I had told you what that was. Okay? So proteins, including hemoglobin, have amino groups on them. One of these is the amino acid side chain lysine. So HB is for hemoglobin, and one of the side chains on hemoglobin is a lysine side chain, which has an amino group on it. Normally at physiological pH, it's present as the ammonium ion, but there's a small amount in equilibrium of the neutral amine. Enter glucose. Here is the structure of glucose in its closed chain cyclic hemiacetal form. If those words don't mean anything to you, they will very soon. But glucose is in equilibrium with an open chain form that's actually an aldehyde. And we're going to talk about that soon. For right now, just accept that glucose is an aldehyde. Now you can understand why biology, and your body in particular, wants to control glucose levels so tightly. And the reason for that is, though you use it for energy, it's an aldehyde, and that's at our top level of carbonyl compound reactivity. So you don't want that aldehyde present in large amounts, because it can start doing undesired things, one of which is imine formation with lysine side chains of various things. Hemoglobin is just one of the proteins that's in your blood, so it's easy to measure. But you can imagine that forming imines on groups that are supposed to be positively charged might actually change the structure and function of some proteins. So here is hemoglobin, here is the lysine side chain, and here it now is an imine attached to glucose, where R here equals the rest of glucose. Okay, and so there are now great analytical methods for measuring how much of this glycated hemoglobin is in your blood. It's a good measurement. Your red blood cells are recycled at a certain rate and hemoglobin persists. It's a good average measurement of what your blood sugar has been over a longer period of time versus what you can measure for your blood glucose just right now. In some proteins, the presence of these imines lead to what are called AGEs, or advanced glycation end products. I won't show you any of that chemistry, but some of these are related to some problematic situations. It's one of the reasons why you want your blood glucose to be pretty controlled. Another example of an imine that's involved in all of you being able to see what we're drawing today is present in your rhodopsin proteins in the rod and cone cells of your eyes. So I'm going to draw this. And by the way, when I talk about biology, inevitably someone asks, I know you're out there trying to not raise your hand, but someone's going to ask, so how much of this is going to be on the test? My answer to that is everything I say is important. Is all of it equally important? Yes. Maybe not. But I clearly don't want you to memorize structures, but I do want you to understand enough of what we're talking about so that when you take the test, it will appear to me as though you were in class today listening. Is that sort of fair enough? Okay, so I'm going to draw the structure of a molecule that's important in vision. I don't want you to memorize this structure, but you should understand that it's an imine, and you should be able to pick an imine out of a lineup. So this, what I'm going to draw for you, is called 11-cis-retinal. It's an aldehyde. It has a cis double bond in a conjugated backbone. And then the aldehyde, which would normally be here, is actually attached via an imine linkage to, you guessed it, a lysine side chain in the larger transmembrane protein rhodopsin. And this is in your rod and cone cells. This is the molecule that actually absorbs a photon of light, which creates the image impulse. And it's actually multiple steps, but it happens really fast. So you have this cis double bond, and the molecule is highly, I'm missing a double bond there, highly conjugated. That means the energy gap between the HOMO and the LUMO of the molecule is low enough that a photon of light in the visible region can excite an electron from the HOMO to the LUMO. That photon is absorbed. When that happens, it weakens the double bonds in this conjugated system, and this sterically hindered cis double bond, the protons from the methyl group and then that proton get in the way of each other. When you weaken that double bond, the molecule snaps open to a trans configuration. So here's what that would look like. I don't know why I'm drawing it, because I think you could pretty well visualize it yourself, but why not? There's the now trans double bond. All right. And it turns out that change is a big enough change inside the protein that this brings this group bumping into something else that changes the shape of the protein. It's a transmembrane protein, a voltage-gated receptor kind of thing. It lets a membrane potential in, and that causes the visual signal that's picked up by your optic nerve and then interpreted in your brain. And all of that's happening so fast that you continue to see even while I was explaining it to you. All right? That's kind of cool, imine formation. Now, it turns out that once you get this, what's called photoisomerization from cis to trans, that particular protein of rhodopsin is no longer useful for vision. It needs to be exported to the retinal pigment epithelial cells, which actually come in and have enzymes that hydrolyze this imine linkage, pull out the 11 cis retinal, 11 trans retinal, rotate in, swap in 11 cis retinal, and then traffic that protein back to your rod and cone cells so that you can continue to receive signals. Now, you got tons of these proteins in your rod and cone cells, so you don't often run out of 11 cis retinal, but there is something called photobleaching, and if you've looked at a certain light for a long period of time, you get an after image, and in some ways that's related to the exceeding the capacity of your rod and cone cells to keep up with swapping out some of this aldehyde. Okay? All right. You probably want to know more, but that's all I know about the subject. So anything else? All right. One more thing on imines. This is really kind of cool, and it's in chapter 14. It's related to an aldehyde which we will call PLP. That stands for pyridoxal phosphate. This is a cofactor in some enzymatic reactions. I think you should be able to pick it up out of a lineup, though I don't care that certainly, because on a multiple choice test, you're not going to be drawing anything from scratch. You won't have to sort of memorize its structure without any aid. Though again, I suspect if I were to ask the question, which of the following is PLP, you should be able to do that. Notably, the key functional group is the aldehyde. And biology uses PLP as a carrier for amines. In particular, it uses it as a carrier for ammonia or NH3. There are a lot of times where biology needs to move NH3 around, but if you have high levels of ammonia in your blood, that's usually a bad thing. I am not a physician, so I don't know what it actually entails, but I think it's acutely toxic. So your body needs a way of transporting and dealing with ammonia. You excrete ammonia in a molecule that's called urea in a sort of innocuous form that isn't going to do any damage to anybody. But sometimes you need the ability to move an amino group around, and biology uses imines to do this. So what I'm going to show you, you're going to hate. It's in your text, so there's plenty of time to review it. And I'm going to not push the arrows through imine formation because I want to give you the overall sense for what's going on here, and you've already seen the mechanism for imine formation. So here is an amino acid called, well, we don't care what it is because there's the R group. Any of the amino acids, and they exist in this form where the carboxylate's negatively charged and the amino group is in its ammonium form, although there'll be a small amount of amino form at various stages. And let's just say that this is alanine. Let's put a methyl group there, and then this is the amino acid alanine. You don't need to know that now, but before the end of the class, you will have memorized all the amino acids because I told you to, and you will answer questions on the exam about them. So what you're going to do here is imine formation between the amino group on the alanine and the aldehyde on PLP. So we don't need to belabor that point. You could draw the mechanism if I asked you to. By the way, the mechanism would be identical to what we've drawn above, and you are always welcome when drawing a mechanism to abbreviate the parts of the molecule with R's or whatever for things that aren't involved. The group that I'm drawing now, that's a phosphoester. We won't say much about that at this point. I'm not drawing its Lewis structure. It's not really a part of the story at this point. There's a methyl group here. Here is the nitrogen of alanine. And then here is the carboxylate, and then there's the CH3 group. I didn't change any stereochemistry there. I just moved some stuff around. You'll have to trust me that the stereocenters are correct. Okay, so there is your imine. Now, so far, so good, but what I told you is biology wanted a way to steal the amino group from alanine. The next step is what does this. Okay. We've made the imine. Now let's call this the carbonyl carbon and this the alpha carbon. Look at this proton, and I'm going to sometimes we don't have to show the CH3. That wedge just means a CH3 group. Hopefully you're okay with that. Here's the proton on the alpha carbon. Now notice that proton is adjacent to a carbonyl here. It's also adjacent to a pi bond there. And if we removed it, the resulting negative charge would be delocalized by resonance. And so a basic group from the enzyme can remove this proton that's on the alpha carbon. And I'm first going to draw the resonance structure where the resulting negative charge in the conjugate base is still on that alpha carbon. But you're going to see quickly, using your 351 resonance intuition, that negatively charged proton is highly delocalized by resonance. All right, so here is the alpha carbon. There's the lone pairs that used to be in the carbon hydrogen bond. Here's the methyl group from your alanine side chain. For completeness, here is the conjugate acid of whatever basic group did the deprotonating. Notice how that positive charge is delocalized by resonance. We could draw resonance structures, I'm sorry, it's a negative charge. We could draw resonance structures where that negative charge would be here on the oxygen. Where else could I put it? Bounce it here to form a pi bond between carbon and nitrogen, but then what would I have to do? Bounce it here. Yeah, go ahead.
What happened to the positive charge on nitrogen?
It should still be there, sorry, thank you. Yep, there's still a positive formal charge on that nitrogen. Yep. Okay, where else? If you remember my evil 351 exams, it's alternating atoms, right? And in fact, I could draw a resonance structure of what I just showed you that would look like this. I'll push the arrows so you can see where it comes from. But we can draw a neutral resonance structure, or rather a resonance structure where the negatively charged, sorry, I'm struggling with that nitrogen, where the negative charge from the alpha proton is actually delocalized over a wide area. Here's the phosphoester still. Here's the nitrogen. Okay. In some ways, PLP serves as, did I get anything wrong? I think we're good. Do you see anything? In some ways, PLP serves as what we might call an electron sink. It's a place for the negatively charged electrons on the alpha carbon to go. But importantly, look at what changed when we removed that proton. The imine used to be between the nitrogen and this particular carbon of PLP, right? Now it's still an imine, but the imine is on the other side. In other words, we have turned what used to be the alpha carbon of an amino acid into an aldehyde, or an imine equivalent. So at this stage, what we can do is hydrolyze that imine, and remember, when we hydrolyze an imine, this carbon becomes an aldehyde, and this becomes an amino group. So I'm not going to draw the mechanism for imine hydrolysis, but because you've seen it before. But the key point here is that nature has used PLP to basically extract ammonia, an NH3 group, or an NH2 group, from an amino acid, and at nowhere during the process did we ever generate free ammonia. Left over here on the other side is your aldehyde or ketone. I guess I should have been specific. When you look at an imine, you can tell whether it's going to have come from an aldehyde or ketone by looking at the two things attached. If they're both carbons, it was a ketone. If one's carbon and one's a hydrogen, then it was an aldehyde. So here is the thing that's left over after we do imine hydrolysis, and this is actually called pyruvate, which nature can have a bunch of other uses for. In fact, we saw it earlier last time. We saw the oxidation or reduction of pyruvate into lactate. Note that in the beginning, the amino group was on alanine. Now the amino group is on PLP. In this form, this is called pyridoxamine, and this can be used in a lot of other places for a lot of other purposes. In fact, if nature wanted to, it could take pyridoxamine and now go to a different molecule. Suppose you had not pyruvate, but some other ketone. Nature could install the nitrogen there, and then you'd have the amino acid phenylalanine. And this is involved a ton in amino acid metabolism. Okay, questions about that? Let me answer the one you want to ask. Is this going to be on the test? Yes. What's going to be on the test? Draw the structure of PLP. No, because you're not drawing anything. Pick it out of a lineup, multiple choice. Sure, that's fair game. What about mechanism? Could I ask you, given some options, which of these is a reasonable mechanistic step? Absolutely. Should you know imine formation, imine hydrolysis? Yep, no problem there. Other questions? All right, we've beat to death imines. Yeah, go ahead.
Can you go backwards in this?
But they're not dead yet. Go ahead, Miriam. Where are we going?
Backwards, were you ever, like, hypothetically on a test say, oh, what's the mechanism backwards for the PLP?
Oh, if you want to go backwards, could I ask that? I mean, this direction is imine formation, this direction is imine hydrolysis. Going backwards would be imine formation versus imine hydrolysis. So yes, in the sense that you should be able to do imine formation and imine hydrolysis both ways. Yep. All right. What else? Yeah.
I had a question on the enemy. Is that what you said?
Sure. Enamine. You got to go a little nasally, but that's okay. Plug your nose. Enamine. Yeah. Yes. Yeah, great question. If you had a ketone and the R groups on either side were different, which enamine should you form? That's a great question. I'm not sure how to answer it. We will actually do know how to answer it, but I'm going to punt on it because that's going to be something that we get in a future section, a future chapter of the class. We won't talk about it with respect to enamine specifically, but we'll talk about a related molecule called an enol, and yeah, there is a way to predict, but don't worry about it for now. All right, others? Somebody's pointing, thank you.
So you're saying that the PLP absorbs ammonia, or is that not what you're saying?
I'm saying the PLP transports nitrogen as a way to avoid having to have concentrations of ammonia in your blood. Suppose that I had, suppose I wanted to go backwards. Sorry, I deleted something and now I need to undelete it, but I don't know how. So I'll delete it again. Suppose I wanted to go backwards. I started with pyruvate and I wanted to put a nitrogen there. You might say, why doesn't biology just use NH3 as the ammonia to do this and make an imine? And the answer is ammonia is toxic, so it has this alternative.
Okay.
Yep. Enzymes that do this are called transaminases. So you'll see this kind of thing a ton in biochem. All right, what else? Yes?
Is there any situation that it would become aromatic like the PLP at the beginning instead of staying with the electrons on the end?
Ah, good. Yeah, so you're noting that here, this is an aromatic ring, and we haven't necessarily talked about what that means, but a six-membered ring with alternating double bonds is a pretty good indicator. You'll notice that we don't necessarily have that here. We could draw a resonance structure where this would be aromatic and we'd have a negative charge on this carbon, and that would be fine. So, yeah, I don't totally know how to answer the question as to how stable this is. Is it uphill in energy to go here because you're destroying a little bit of aromaticity? Maybe a little bit, but I don't know. It's a good question. Okay, others? All right, so what we're going to do now is let's, instead of using amines as nucleophiles, let's use water or let's use alcohols. Oh, sorry. Here is an aldehyde. Here is a ketone. And it turns out that in the presence of water, these two are in equilibrium, very small amount, with something that looks like this. And this is called an aldehyde hydrate. It's called that because we've basically added water to the aldehyde. If you want to know where the water is, there's one hydrogen and there's the OH group. And of course you can do this with ketones too. You don't have to try to do this if you have aldehydes or ketones in aqueous solution, X percentage of or Y percentage of the ketone is going to exist, or aldehyde is going to exist in the hydrate form. Formation of the aldehyde hydrate or the ketone hydrate can happen under basic or acidic conditions. It can even happen at pH 7 where you don't have very much acid or very much base involved at all, but you have enough to get the reaction going. So let me show you a mechanism for acid catalyzed hydrate formation. Probably you would need some small amount, and again, even the small amount of H3O plus that's present at pH 7 is good enough. You protonate the aldehyde first. You have to do that because the aldehyde itself, water is not a good enough nucleophile to attack the aldehyde directly. You protonate it to get to this oxonium ion, which now is reactive enough for water to attack. That gets you this tetrahedral intermediate where the water that just attacked is now got a carbon-oxygen bond, 3 things bonded to the oxygen, so it has a positive formal charge. And in the final step, the conjugate base of H3O plus will remove a proton to get you to the hydrate. I am not going to draw the backwards reaction because I think you can do it on your own. If you can do imine hydrolysis and formation, you ought to be able to do the backwards of hydrate formation. Pretty simple. Protonate the carbonyl oxygen, then water attacks, then you remove the proton, and that gets you to your neutral aldehyde hydrate. There's another word that we could say to describe this molecule. It is a gem diol. Geminal, gem is an abbreviation for geminal. That means on the same carbon. If that word sounds familiar, it comes from the same Greek word that we use to describe the constellation Gemini, the twins. And there's a lot of languages, Spanish among them. Gemelos is twins, same word. Twin oxygens on a carbon. Okay. The mechanism for the ketone is exactly the same, so we don't need to show it. Let me show you briefly, if you wanted to do this under base catalyzed conditions, what that would look like. You would use OH minus, which is a good enough nucleophile to attack the carbonyl carbon directly. That would give you this intermediate with a negatively charged oxygen, which would then pick up a proton from water, thereby regenerating the base catalyst. And that's why you don't need very much base at all for this to happen, but you end up with the same hydrate product. Your text, I don't think, makes a big point here, but it is true in organic chemistry that you can use this percentage for how much hydrate is formed as a measure for how electron poor a carbonyl compound is. So an aldehyde is more electron poor than a ketone for reasons we've already discussed, and therefore the percent hydrate formation for the aldehyde is greater than the percent hydrate formation for the ketone. So you may face, I'm not sure, but in end of chapter problems, or perhaps, I don't know, it's possible that someone on an MCAT or a DAT might ask you which of these should have a larger formation of hydrate. And that's the same thing as asking which of these is the most reactive carbonyl compound. All right, hydrates are boring. There's not too much you can do with them. So I don't want to spend too much time on them. But any questions? I've already told you they were boring, so if there aren't any questions because you don't care anymore. That's fine. All right, next one's a little bit harder. We're going to be using not water, but alcohols to react with carbonyl compounds. Okay? When you add alcohols to carbonyl compounds like aldehydes or ketones, the resulting products are called acetals. And like imine formation, you need an acid catalyst for this to happen. Your starting material is an aldehyde or a ketone. You need an alcohol, which is going to be your nucleophile. You do not expect the neutral alcohol to be able to attack the carbonyl carbon directly, so you need a catalytic amount of acid. And again, potential candidates for this catalytic acid include organic soluble acids like acetic acid, or even the much stronger toluene sulfonic acid, or TSOH. When you do this reaction, you end up replacing each of the carbon-oxygen bonds in the starting material with carbon-oxygen bonds involving the alcohol, and you end up losing water. And if you want acetal formation to occur, you probably need to remove the water from the equilibrium, because this is an equilibrium process and you can go backwards. And we will see that if you start with the acetal, you can go backwards by simply using an aqueous acid, where you have a large excess of water, and that's going to release your aldehyde or your ketone, and it's going to release the alcohol. Just as a preview, these reactions are so efficient that this acetal formation or hydrolysis strategy is used as a protecting group strategy for both ketones, aldehydes, and even alcohols. And so this shows up a lot in organic chemistry. So that's the overview. Let's do mechanism. All right, so we'll start with our aldehyde. Again, you expect that the alcohol is not, a neutral alcohol is not a good enough nucleophile to attack directly. And there's evidence that for acetals, and actually you even expect the alcohol to be less of a good nucleophile than an amino group is, because oxygen's more electronegative than nitrogen. So as opposed to imine formation, recall that with imine formation we attacked with the nitrogen at the same time as we protonated. It turns out that there's good evidence that acetal formation is something that we will see, you'll see in biochemistry. It's called specific acid catalyzed. That means you have to protonate first. And then in the second step, the nucleophile attacks. So the first step of acetal formation is protonate the carbonyl oxygen. I'm going to use equilibrium arrows to remind you that we're going to be going forward, but the reverse is also possible. That generates this oxonium ion, which is what we call the protonated carbonyl. At that stage, the alcohol is a good enough nucleophile to attack the pi star to give us a tetrahedral intermediate. Though you'll notice that this tetrahedral intermediate, like its oxonium ion precursor, is also positively charged, just on a different place. Now it's the alcohol oxygen that's positively charged. Okay. And then we can regenerate our acid catalyst by having the conjugate base of our acid remove the proton from the oxonium ion. And that takes us to this neutral intermediate. If you are thinking by analogy to imine formation, for the imine we called that a carbonylamine. For acetal formation, this molecule has a specific name that's going to come up a lot in a lot of different places, and that is hemiacetal, meaning halfway to an acetal. The acetal has two methoxy groups or two alkoxy groups on what used to be the carbonyl carbon. The hemiacetal has one. Okay. So if you're following along, yeah, we got two here, and they both come from here. In the hemiacetal, only one is attached. The other OH group used to be the carbonyl oxygen, so it's still there. Hemiacetals are generally not that stable. They're sort of semi-high energy intermediates relative to both starting materials and products. So molecules generally don't stop at this stage, with one important exception, and that is the carbohydrates like glucose, which I just showed you previously. We're not going to get to them today, but we will next time. Now, how do we get to that acetal? We want to replace this OH group with another methoxy group. To do that, we're going to want this OH group to leave, but it can't yet because it's not a good leaving group, or at least a neutral oxygen kicker-offer is not a good enough kicker-offer to kick off a negatively charged OH. So we will use our acid catalyst to protonate the OH group, thereby turning it into a good leaving group. We've got a new oxonium ion, this time with a positive charge on the oxygen from water. Now this is a good enough leaving group, and the neutral kicker-offer can kick off water as a leaving group. That is the stage at which we lose water. And run out of space, so we'll curve this downward. What's left, if you're thinking back to imine formation, looks very similar to that iminium ion. For imine formation, there was an NH bond that we could remove to deprotonate this molecule. It turns out, though, that this is another example of an oxonium ion, a positively charged carbonyl oxygen, is highly electrophilic, and a second molecule of alcohol will come in and attack the carbonyl carbon, breaking the carbon-oxygen pi bond. That installs our second methoxy group. It's got a positive charge on it because it came with the hydrogen, and we can use the conjugate base of our acid to remove that proton, and that will get us to our final acetal product. That's a ton of steps. That may be the longest mechanism you've got so far in organic chemistry. So I congratulate you, but I warn you that much bigger heights are in your future. So now's the time to build up the endurance. Okay, questions about that? Yes?
Why wouldn't the alcohol pair attack the positive charge?
Why doesn't the lone pair on the alcohol attack the positive charge? The reason for that is that oxygen's more electronegative than carbon, and so much of that positive charge is actually felt on the carbonyl carbon. Okay, that's enough for today. Have a good weekend. See you Monday.